Okay, so this is our 1.11 notes. We're going to read this little blurb about blood pressure. Now, I don't expect you guys have suddenly, like after sleeping last night, have turned into scientists. So we're going to try to figure out what the important pieces of information are from this blurb, okay? Because it's going to have a lot of crazy vocab in it. Blood pressure is a measure of the pressure or force. Pressure is actually force per unit of area, so I object already to this problem. That's fine. Of blood against the blood vessels. There are two measurements usually provided for blood pressure. Systolic blood pressure is a measure of the pressure in the blood vessels during a heartbeat. Hey, while diastolic blood pressure is a measure of the pressure in the blood vessels between consecutive heartbeats. Suppose a study tracked diastolic blood pressure for 40,000 participants. Okay, the results showed that the blood pressure measurements were normally distributed. With a mean of 80 millimeters mercury. Okay, 80 millimeters of mercury and a standard deviation of 10 millimeters mercury. Okay, note that millimeters of Hg stands for millimeters of mercury, which is 1 unit to measure pressure. So what they have, guys, is like a little instrument, and it's marked off in like millimeters, okay? And the harder your blood pushes, like the more millimeters of mercury you get. Does that make sense? Yeah. Okay. So we are going to complete this diagram using what we know about normally distributed data. So if it's normally distributed, what rule do we have the benefit of being able to apply? Starts with an E, it's impossible to spell. Empirical. Yes, empirical. So we are going to use the empirical rule, which we are going to write over here. Now today is a write small day, at least for this diagram part. The empirical rule. Okay, it says that within 1 standard deviation is how much of your data? 68%. 68%. Okay, what about within 2 standard deviations of the mean? 95%. Okay, what about 3? 99.7. All right. Okay, now let's start labeling. We're going to come back to the empirical rule. So what do you think goes in this like very, very middle box? Median, like 68%. What value is going to go here? Oh, the mean. The mean. So this is your X bar, which in this case, what did it say it was? 80 millimeters mercury. Okay, what did it say the standard deviation was? 10. So how are we going to find out what to put in these boxes? Go up and down by 10. Yeah, up and down by 10. So 90 millimeters of mercury. Nope, it says we have to label. Sorry. 100 millimeters of mercury and 110 millimeters of mercury. All right, then we'll go backwards. We'll subtract tens. So 70, 60, and 50. Okay, does everybody know how we got that? Perfect. Now, this is 68% of our data, right? Mm-hmm. Okay, but it's chopped in half by our mean. Okay, so what percent of our data is over here under this part of the curve? What's half of 68%? Correct. And this would also be 34%. Okay, now to do these other ones, we're going to have to do a little bit of trickiness. So we can divide all of these in half to see which part, like how much is on one side or the other of the mean, right? Okay, so half of 68 was 34%. What about half of 95? It's going to be more than 45. Yeah. 47.5. Good. 47.5%. What about half of the 99.7? Good. 0.85. Good. Okay. So now that we have that information, we know that this piece, oh my gosh, this piece right here is the 47.5, right? Because it's half of the 95. Do you guys see what I'm looking at? Okay, so here's one standard deviation and -1. Here's 2 and -2. Okay, so plus or minus 2 standard deviations, we said that that was 95% of our data. And if we're just looking at this side, isn't this 47.5? Everybody see what I'm talking about? Mm-hmm. Okay, so this is 47.5%. And if I want to find this part of that, don't I just subtract away that 34? Okay. 13.5, you said? Yeah. Okay, so if this side is 13.5, what is this side? All right. Also 13.5%. All right, we're going to do our little trick again. Okay, so here is our third standard deviation. That's our 3. And over here is our -3. Okay, so 99.7% of our data falls within 3 standard deviations of the mean. Half of that is what? Okay, so this side right here is 49.85%, but I don't want all of that. I want to take away this 47.5%, the pink part. Does everybody see what I'm doing? So I'm going to subtract the 47.5, and what do we get? I think it's like 2 something. Like 235? Yes. So 2.35%. So this side is 2.35%. So is this side. That's what percent of the data falls under that curve in that section. Okay, last one. Hard part is almost over. Okay, isn't 50% of our data over here? Okay, so this little section is going to be half of our data, 50% minus the orange, the 3 standard deviations. Well, half of the orange. So minus the 49.85. Which is 0.15%. So that's what that side is too. Huh? Oh. No, not yet. We haven't talked about what to write in the boxes yet. We're just talking percents. Okay, now that we have the whole thing ready to go, it says fill in each box under the horizontal axis, that's this, with the appropriate measure of pressure. So we already did that. Then fill in each box representing an area under the normal curve with the approximate number of people. Okay, so we need to know what 34% of what? How many people?
40,000.
Okay, so we just have to figure out what 34% of 40,000 is. What did you guys get?
13,000.
Good, that's what I got.
Oh my goodness.
What? Okay, that one has been broken. Yes, it's very. I think so. Is that one newly shattered?
I don't know.
Okay, one of them was shattered already. Wait, oh, can I see it? Yeah, I think that one was already broken. You can still read it, right? Okay, next one. What is 13.5% of 40,000?
40. Wait, no. Oh, I did that. Okay.
Put my big head in front of it so you can't copy off of me.
5,000.
Yes, that is correct. All right, next. What is 2.35%? Okay, so whenever we're doing this, guys, remember that we're multiplying and moving the decimal point over by 2, right? Okay. It's like you're drawing a cute little butt. All right, we're ready.
9,000. No. 940. 940.
That seems a little high. Did you move the decimal point over 2 times?
Oh.
So you should be doing 0.0235 times 40,000.
Yeah. 940.
Is it really?
Yeah.
Okay.
I was like, I don't know what I did.
All right, let me. Maybe I'm the one who's like losing my mind. 0.0235 times 40. Okay, yeah, it's 940. Sorry to have doubted. All right, last one. Be careful because this one is going to be 0.0015. Yeah, that one I got right. I forgot to do it over here too. So this will be 60 and this one will be 940. Okay, does everybody understand where the heck all of those numbers came from?
Yes.
So it all came from the fact that this is normally distributed. Okay, so we got to use our empirical rule. Cool, cool?
Wait,
Okay.
where'd you get the 0.0015 from?
From moving this decimal point over. Boop, boop.
Oh, you subtracted from it.
Oh, sorry. Did I not answer the right question?
Yeah, I was just trying to see like how we got that, like what we subtracted.
We did 50% of the data
Yeah.
minus like 3 standard deviations worth of data. Okay. All right, so now the fun part. What is the probability that a randomly selected person from the study had a diastolic blood pressure higher than 80 millimeters mercury? So probability of greater than 80 millimeters of mercury is what? 50%, so 0.5. What about lower than 80 millimeters mercury? Yeah, also 50%, so 0.5, 0.5. Okay, so it says that we have to explain. So we know that in any data distribution, the median is our middle number, right? When our distribution is actually normal, the median and the mean should be together in the very middle of our data. So it's not just the median that chops our data in half. When we're normally distributed, our mean splits the data in half. Does that make sense to everybody? Okay. When the distribution is normal, the mean divides the data in half. So half of our data should be above the mean and half should be below. Okay, what is the probability that a randomly selected person
It also asks for equal to, greater than, less than, or equal to.
Oh, they are the same. That's what we forgot to say. The probability is the same. That's what I forgot. Thank you. The probability is the same.
Do you not have to do another equation for equal to, or what's,
Okay, is that probability greater than, less than, or equal to? We're saying they're equal. It's saying pick one. Does that make sense? So we're saying the same. We could have said the probabilities are equal. Okay, can we please put the phones away? Okay, what? Can you guys stop? What is the probability that a randomly selected person from the study had a diastolic blood pressure between 70 and 90? So let's look. Between 70 and 90. According to our empirical rule, that's 68% of our people. Right? So, isn't that 0.68? So, probability of between 70 and 90 equals 0.68 from the empirical rule. What is the probability that a randomly selected person from the study had a diastolic blood pressure between 60 and 100. Whoops, that's a lot of E's. Between 60 and 100. All right, let's look. Okay, 60 to 100. That's within 2 standard deviations. So according to our empirical rule, what is the probability? 95% or 0.95? Yes. Okay, almost done with this page. We're coming down the home stretch. What is the probability that a randomly selected person from the study had a diastolic blood pressure between 50 and 110? Okay, so is that 3 standard deviations? Okay, so 0.997. So all of these, okay, there's a question on the back that says, how are these probabilities related to the empirical rule? Well, duh, I mean, it's basically just the empirical rule. Okay, we're going to skip that one. Okay. All right, guys, this is the same deal. Did you know that women's shoe sizes can be modeled by a normal distribution? In the US, the mean women's shoe size is 8. So this is size 8. And we have a standard deviation of 1.5. So we can add 1.5 and get 9.5, 11, 12.5. And then subtract it, 6.5, 5, brain, 3.5. Okay, and then we want the units down here, so we can label these size. Yeah. You can just label it at the bottom. Okay. Does anybody remember what percent went right here? 34% and 34%. Okay, what about between the first and second standard deviation?
13.5.
Correct? Okay, between the second and third standard deviations? 2.35%. And last?
0.015.
Yeah, 0.15%. Okay. So, it says fill in each box representing an area under the normal curve with the probability that a randomly selected woman in the US has a shoe size in that region of the graph.
It doesn't tell you like how many people were surveyed.
Okay, so let's pretend that we had 1,000 women. Okay, 1,000 women. 34% of them have a shoe size between 8 and 9.5. What is the probability of picking one of those women? So we're going to do 0.34 times 1,000 women divided by 1,000 women, right? Because that's how many we're picking from. It's 0.34? Oh, that's weird. Is it just because I chose 1,000? What do you want to choose instead? 80? How many women do you want to pick out of? 80?
80.
All right, let's try the next one with 80. So we'll do this one with 80. So we'll do 0.34 times 80 ladies. This time we're picking out of 80 ladies. What do we still get? Okay, think about it.
Oh, wait, we're doing yes. Oh, wait, oh.
Do you see that it's going to still be 0.34?
So that's why we don't have like a number.
That's why we don't. Does it matter how many we pick out of?
No.
Okay. Well, because it's out of all. Because you're taking 0.34 out of 1,000, right? Does everybody understand what's happening? It doesn't matter how many you pick out of. Whether I picked out of 1,000 or whether I picked out of 80, it's still the same odds, right? Okay. I could have just told you that, but it's more important that we figured it out. So thank you for working through that with me. I appreciate you.
Oh, I thought we were trying to figure out like how many women need like.
Well, on the front we figured out how many women. This is asking us to find the probability. Okay, so we're going directly to the probabilities. We're skipping the number of ladies. All right, so do you see that we can just move the decimal point over 2 times and then we're going to get what the probability is? So it should be 0.135. 0.135. 0.0235. And then last, 2 zeros after the decimal point. So 0.0015. 2 zeros after the decimal point. 0.0015. Okay, so far so good? Okay. Now the fun part. We have to find the probability that a randomly selected woman in the U.S. has a shoe size between 6.5 and 8. So every time we got to use proper notation or we're going to get dinged. Okay, we don't have extra points to lose, right? So we want the probability of between 6.5 and 8. So 6.5 and 8, what is that probability? It says it right up there.
0.35.
0.34. Is that what you said?
Yes, that's what I'm
Okay. Okay, next one. What is the probability that a randomly selected woman in the U.S. has a shoe size less than 6.5? Less than 6.5. So that's over here. So we can either add these 3 up or we can do 50% minus the 0.34, right? So 0.5 minus 0.34, or we can do 0.0015 plus 0.0235 plus 0.135. Right? We can either add these 3 together or we can take the whole half and subtract the 0.34. Don't overthink it, right? Don't overthink it. Don't you dare. You should get 0.16. Either way you do it. Sometimes subtracting is fewer keystrokes. So, you know what I mean? All right, what is the probability that a randomly selected woman in the U.S. has a shoe size greater than 6.5? Greater? No.
Oh, wait, oh.
So isn't it 100% minus that 16%?
Yes.
Okay, so it's 100 minus 16.
No.
So it's 0.84, good. 1.00 minus 0.16. See, sometimes subtracting is easier. Okay, number 11. What is the probability that a randomly selected woman in the United States has a shoe size between 9.5 and 11?
Or 0.135.
Yeah. Yep, it's real.
It's real.
Okay. Is it more likely? Hey. Okay. Is it more likely to randomly select a woman whose shoe size is greater than 12.5 or less than 5? So we need to find those two probabilities. Probability of greater than 12.5 and probability of less than 5. I can't see my graph anymore. So greater than 12.5, I'm getting 0.0015. And less than 5, I'm getting, thank you, 0.0235. So which one is more likely?
The probability of it being less than 5.
Right. Because those are different standard deviation boundaries, right? This is like 3 standard deviations and this is 2. Does that make sense to everybody? Okay. So probability of randomly selecting a woman whose shoe size is less than 5 is more likely or is greater. So you can say that 0.0235 is greater than 0.0015. So it's more likely to pick the lady with shoe size less than 5. Any questions?
Work time.
Work time. It's Christmas morning.
It is Christmas.